Hello everyone, it's me again. In today's video, I'm going to discuss the organic chemistry behind a particular drug that might sound familiar to those of you who suffer from immunosuppression, such as myself. A medication known to those as Atovaquone. Now, for those of you who are unfamiliar with this and might be asking, what's Atovaquone? Well, Atovaquone is a yellow paint-like liquid medicine that you can only obtain through a prescription, not over the counter. Some of you might be familiar with this med under a different name called Mepron. Or for you organic chemists out there, 2,4,4-chlorophenyl cyclohexyl 3-hydroxynaphthalene 1,4-dione. This is an anti-parasitic class medication that's used in the prevention or the treatment of pneumocystis jirovecii pneumonia, a fungal infection in the lungs that can cause some serious life-threatening breathing complications. While it's very rare for healthy individuals to contract this, those with HIV, AIDS, and cancer are at most risk at contracting this due to being immunocompromised. By taking this medication, they will be reducing the risks of contracting this illness, as well as they'll be also most likely to be receiving these side effects from taking the medication as well. Now that you got the general gist of Atovaquone, let's dive into its organic chemistry. Now, a molecule of Atovaquone consists of 22 carbons, 19 hydrogens, 1 chlorine, and 3 oxygen atoms. As I've mentioned earlier, a molecule of Atovaquone would be called 2,4,4-chlorophenyl cyclohexyl 3-hydroxynaphthalene 1,4-dione. By translating that name into a structure, this is what we'd be mostly expecting to receive. Now, for those of you who don't understand chemistry very well, this is called a skeletal structure. Another way we'd also be able to interpret this would be as a Lewis structure. The difference between those two is that the Lewis structure shows us the carbons within that are holding together in the rings, and as well as the hydrogens that are attached to the carbons. So now let's focus on what makes up the molecule of Atovaquone. As what is present to us right now, we can at least distinguish about the major functional groups that makes up this molecule. What we can see immediately is that this molecule contains rings, ketones, hydroxyl, 1-aryl halide. These 4 functional groups make up the majority of an Atovaquone molecule. Now, let's for example say that you wanted to try to dissolve this molecule. What would be the best type of solution you could use from the choices that we have, which are water, methanol, and hexane? Some of you might be thinking water would be fine because, of course, it has polar bonds and is able to hydrogen bond. And since, of course, the Atovaquone has oxygen and it also has hydrogen donors and hydrogen bond donors and hydrogen bond acceptors, you'd probably be assuming that it could be soluble in water. However, that's not the case, because most of the majority of it is made up of carbon bonds, which of course are nonpolar. So that leaves us with methanol and hexane. So methanol, you'd probably be saying, oh yeah, that could work, because of course it has a methyl group and a hydroxyl group. But in actuality, the one solution that would be most useful in dissolving this would be hexane. The reason for this is because the molecule of atovaquone mostly consists of covalent nonpolar bonds between its carbon atoms within its multiple rings. Although it has two polar carbon-oxygen bonds and a polar carbon-chlorine bond, it wouldn't be soluble in water or methanol because of London forces. These intermolecular forces of London forces, of course, are what's holding it together, as well as the hexane is the only thing that can be able to interact with it, since, of course, the other two are more polar, and hexane is not as polar. But let's say instead we wanted to crystallize this molecule of atovaquone. That then, we'd be using methanol. The reason for this is because atovaquone will be partially soluble in methanol. And since it's partially soluble at room temperature, we can then try to heat up the liquid itself, which would then allow us to completely dissolve the molecule. This would then be breaking the bonds. Now, from that, of course, we can cool the solution back to room temperature, which then will allow it to go back to being partial soluble. And then from that, we can cool it further into being completely insoluble. By doing so, we'd be reforming the bonds, thus allowing it to come back completely recrystallize. Lastly, if you recall seeing my last video on how to find the most acidic hydrogen on a molecule, we could also try to find the most acidic hydrogen on this molecule as well. As you can see, the most acidic hydrogen that would be on this molecule would be the hydrogen that's attached to the oxygen. This is because the oxygen has the capability of maintaining a negative formal charge because of its electronegativity, as well as we can also perform resonance from this structure. As you can see, this structure can produce resonance from the movement of electrons from the oxygen onto the sigma bond. This would then turn into a double bond, thus shifting the double bond on the ring towards the next available sigma bond, which just so happens to be next to another double bond. Now that double bond will then transfer its electrons onto the other bonded oxygen, giving it a negative formal charge. By maintaining that, we are able to perform resonance, as, of course, we still maintain that negative formal charge. Well, it seems like that's all the time we have for today. Thank you for watching, and I hope you've learned something interesting about atovaquone.